Hi, everyone. We're going to be talking about balancing redox reactions today using the half reaction method. So let's jump right in. So this procedure, which works on every redox reaction, involves a few steps, which if you follow them in order, you'll never make a mistake. So the first step is we write down the half reactions. And that means we look at the things that are going to be reduced and oxidized, and we separate them into two separate half reactions. Now, it doesn't matter if we don't know right away which one of these is the oxidation half reaction and which one of these is going to be the reduction half reaction. We're actually going to figure that out in a later step. So I just identified the two different species, the manganese here and the sulfur. They're the ones that are going to be either oxidized or reduced, and we're going to keep going. So at this point, for both of these half reactions, we're going to balance everything that's not a hydrogen and not an oxygen. So we're talking here about the sulfur in this half reaction and the manganese in this half reaction. Now, it happens to be in this one, they already are balanced 1-to-1 and 1-to-1. But if not, we would balance those here now. We wouldn't do anything other than just change the coefficients for all of these. So these coefficients are going to stay. Step 3 is we're going to balance all of the oxygens using water and only water. So, for example, here we have 4 oxygens on the left-hand side of the reaction. We have none on the right-hand side. So we're going to have to add oxygen to this side. And we're going to do that by adding 4 waters. That's going to also give us 4 oxygens. We're done with oxygens there. Let's look at the second half reaction. Pause the video for a second and figure out, are you adding water to the left or the right? Or maybe you're not adding water at all. And if so, how many? So hopefully you identified that there's 3 oxygens here on the left-hand side, and there's 4 oxygens here on the right-hand side, which means we need another oxygen on the left-hand side. So we're going to add water because we only add water in step 3, nothing else. And so we add 1 water, and now we are satisfied that all of the oxygens are balanced. So at this point, we've balanced everything that's not a hydrogen or an oxygen, and everything that's an oxygen. And now all that's left is to balance the hydrogens. So now we're going to go and look to see if there's hydrogens in our equation. Now, there weren't any before we got started, but in the process of adding waters, we added hydrogen atoms. So to solve this, we are going to add H+. Now, we're going to talk in a little bit about what to do about that H+, because we're not going to leave the H+ floating around over here. But for now, we're going to use the H+, and we're not going to do anything else but H+. So here, there are 8 hydrogens, right? 4 times 2, there's 8 hydrogens on the right-hand side, which means I'm going to add 8 H+ to the left-hand side of my first half reaction. Pause the video right now and ask yourself, how many hydrogens do you have to add and to where in the second half reaction? So we have here 2 hydrogens on the left-hand side of this half reaction, which means we're going to have to add 2 hydrogens on the right-hand side. Now, you may be tempted to think to yourself, well, why couldn't I add H2 or H2SO4 or any other compound that contains hydrogen? Don't do it. Resist the urge. Follow the procedure, and you'll never make a mistake. All right, at this point, we're actually done with adding all the atoms. If you check right now, you got all of the right atoms on both sides. Manganese, manganese, sulfur, sulfur, oxygen, oxygen, hydrogen, hydrogen. Nothing is going to be unbalanced. The only thing that's unbalanced is the charge. So let's jump in and look at the charge of these reactions. Now, if you look at the left-hand side, you have a negative charge here, so that's -1. And you have 8 positive charges here, so that's +8. So the total charge on this side of the manganese half reaction is +7. Look at the other side, though. That's +2, and there's no charge on the waters. That charge doesn't balance out. The only way to get these charges to become the same is with electrons. So think to yourself, where do we add the electrons? We can only add, so where do we add electrons? Do we add electrons to the left-hand side or to the right-hand side? If you said we add them to the left-hand side, you're exactly right. See, adding 5 electrons to the left-hand side adds a -5 over here. And now the left-hand side is +2, and these two match. And now our half reaction is balanced. And not only that, because we're adding electrons to the left-hand side, we've actually identified that this is our reduction half reaction, which is really, really neat. Let's do the same thing for the second half reaction. Pause the video, figure out what the charge on both sides is, and then where you add electrons and how many electrons to add. Hopefully you found out that this side is -2, this side is -2, and then +2. Remember, the coefficient in front gives that. So this side is going to be 0. This side is -2. The only way to fix this is to make this +2 electrons over here. And now we have our balanced half reaction where all of the charges and all of the atoms have finally become equal. At this point, we recognize also that having added electrons to the right-hand side means that this is an oxidation, which is exactly perfect what we expect. One of these had to be oxidation, one of these had to be reduction. So whew, we got it right. Now we're going to take one of the final steps, which is to make sure they are the same number of electrons. We can't combine these two together until such time as they're the same number of electrons in both of the half reactions, because it's the electrons that are given off in the oxidation that are actually absorbed in the reduction. So they have to be the same. So notice we have 2 electrons that are released in the oxidation. We have 5 that are absorbed in the reduction. So what we're going to do is we're going to look for the least common multiple. The lowest common multiple of 2 and 5 is 10. So I'm going to multiply this half reaction by 2, and we're going to multiply this half reaction by 5. And for my benefit, what I always do is I always go through and I rewrite the entire half reaction. I'm less likely to make a mistake when I'm doing the combining, which is the next step, if I've rewritten the half reaction. So this is what we're going to do. So we're now going to multiply through by 5. Don't forget to multiply literally every single thing in here by that 5. And at this point, you should check yourself and you should make sure that the atoms are still balanced on both sides and that the charges are still balanced on both sides. Multiplying them should not have changed anything. And in fact, we see that we are set and ready to go, which brings us to our second to last step, which is we're going to combine these half reactions and then we're going to cancel things out. So let's combine them. So 10 electrons plus 2 permanganates plus 16 H plus, now we got to the arrow. Let's go to the second half reaction. 5 sulfite, 5 waters. Okay, we got to the arrow a second time, so now we'll actually draw our arrow. 5 sulfates, 10 H plus, 10 electrons. We got to the end, so we'll go back and finish the other half reaction. All right. We notice, though, in the process of combining that we have some things that appear on both sides. And this is a good thing. This is actually going to help us out a lot. The first thing that I do is I make sure that the number of electrons on both sides is the same. If it isn't, we've made a big oopsie. But the good news is that they are the same. They cancel out. We're good. When it comes to the H pluses, you see that there are some on the left, some on the right. We're going to cancel out the 10 that are common on both sides. That leaves us only 6 on the left-hand side of the reaction. What about the water? You see that there's waters on both sides. Take a moment, pause the video, and see how much water is left and what side is it left on. We see there's more water on the right-hand side than on the left-hand side. So we cross out the 5 waters that are in common on both sides. And this gives us our full combined redox reaction. Now, I want to point something out. If all you care about, if all that we're looking for is the stoichiometry of the reaction, let's say we're doing a redox titration, if all we cared about the stoichiometry, the reality is at this point, we're done because the stoichiometry is not going to change from this point forward in the process of balancing this redox reaction, right? It's a 2 to 5 reaction stoichiometry between permanganate and sulfite, and nothing's going to change that. But for those of you like me who are saying to yourself, H plus doesn't just float around in a chemical reaction, you're exactly right. In an aqueous reaction, those protons are going to be very, very quickly grabbed up by any waters. And in fact, that's what we could do to finish this redox reaction. And so we're going to replace all of these H pluses with the hydronium ion, which is the acidic species in aqueous solutions. How do we do that? Well, we remember that H plus H2O makes hydronium ion. So if that's the case, if I want to turn those 6 protons into 6 hydronium ions, I need to add 6 waters. So I'm going to do that. I'm going to add 6 waters right here, and this is going to become hydronium. But if you're yelling at your screen right now saying, but Professor Abrams, if I add water to the left-hand side, it's going to be unbalanced. You're exactly right. We have to add the same number of waters to the right-hand side of the reaction. And so now we get 2 permanganates, 5 sulfites, 6 hydronium ions going to 2 manganese 2, 5 sulfate, and 9 waters. And of course, at this point, you should probably put the states for all of these. They're all aqueous except for the water, which is a liquid. And this would be a correctly balanced redox reaction. Now, of course, sometimes we do redox reactions in basic conditions. Well, in basic conditions, we're going to follow a very similar logic. And the similar logic that we're going to follow is if there would be an acidic proton just floating around, it would very quickly react with a hydroxide ion to make water. So let's do that. How many hydroxide ions would react with those 6 protons? Well, 6 hydroxides, you say. Now, for the same reasons as last time, we would need to add now 6 hydroxides to the right-hand side, because otherwise the reaction would not remain balanced. Let's see what that gets us. So we still have 2 permanganates. We still have 5 sulfites. And remember, this is why I pointed out before, the stoichiometry is not going to change. Nothing about the stoichiometry of this reaction changes at this point. Now, 6 protons and 6 hydroxides don't make hydronium. It actually makes 6 water. We still have our 2 manganese 2. We still have our 5 sulfates. We still have 3 waters because those haven't gone away, but we now have 6 hydroxides. I'll point out that these 3 waters and 3 of these cancel out. And if we then finish off, this is our now balanced redox reaction in basic conditions. And this would be our balanced redox reaction in acidic conditions. Thanks for tuning in. I hope that was helpful.